All right. All right. Thanks for holding with us, everyone. Looks like the slides work. So I'm a principal engineer on the Citus cloud team. Before that, I was at Heroku Postgres doing much the same thing, using delivering Postgres over as a database as a service. If you have any questions after this, Twitter's a good bet. Leinweber there. My website is very good, but please, if you're going to visit, I see some people with laptops, mute your speakers because it does autoplay MIDI, because it's a very good 90s website. So I mentioned that this talk is going to be about distributing Postgres, and why do we pick Postgres over some other databases? This is job postings on Hacker News, what technologies that they mention that they're looking for. And it's only goes to last 2016, but the trends have been pretty consistent since then. And Postgres is being mentioned more and more and more over time of what these companies are looking for. Now, of course, Hacker News is not the entire industry by any means. It's only companies that are in YC and those sorts of things. But as a measure of what is becoming popular and where a lot of the interest lies, it's somewhat of a good proxy for that. And so that makes me think it's worth diving into more of these concepts in Postgres. And then the other thing to think about before that we get into the talk is that as you're building an application, it can go down one of a couple different paths. One, you start with a SQL database and you leverage all of the tools, transactions, strong data types, and so on, and you build your application on there. And then historically, people would get their application bigger and bigger and bigger, and then all of a sudden they find out, oh, we can't scale anymore. We can't buy a big enough machine to handle our data. And then they're stuck migrating off to some NoSQL solution, which is an expensive and difficult and long project. Or companies look at others who have gone through that, or they've gone through that process themselves, and think, oh, I know this time I'll start with NoSQL, and that way, once I get big enough, I won't have to do the transition. And that's all well and good, except often applications don't actually get big enough, and you've been throwing away all of your opportunities to have a nice SQL database in the meantime when you may or may not actually get to that scale. And so what's interesting is perhaps there's a third way of starting with SQL and being able to continue and stay with SQL as you scale, and by then moving into a sharded or distributed Postgres. So Citus horizontally scales out Postgres across many, many machines using both sharding and replication. For the sharding, we can route a query to wherever the data lives, in the case of a query that only needs to touch one subset of your data. For example, if you're a multi-tenant application and every tenant has its own view of its own data, if a query comes in only for that one tenant, it can be sent just to that one shard. So that's routing the query. On the other side, if it's a query that does need to touch all of the data in your database, Citus can split that query up and run the individual parts in parallel across all the machines in the cluster, and then aggregate the data as necessary. So the sharding is something that you can do yourself. Often the routing sort, a lot of people, when they need to shard a SQL database, they'll put that in their application. They'll develop logic themselves to know what shard or what database server a particular customer's data is on, and then go there. But it is nice to have the database do that for you in a common interface. And then you can use Citus 3 different ways. The first one is it is an open source project. You can get it at github.com/citusdata/citus. You can get the source code. You can build it yourself. There's also many packages for common operating systems and platforms. There's a fully managed cloud service, which is what I joined Citus to build. And so if you don't want to run it yourself, you can use what I've made, and we run it all on Amazon. And then there also is an enterprise package with some enterprise support plans and so on and so forth. So a very simplified view of Citus is this. In one sense, Citus really doesn't do that much to Postgres. That is, the worker nodes on the what side is this? On the right here and on the coordinator node on the left are all just Postgres servers that have the Citus extension. So a user or an application connects to the coordinator, issues a query, ran through the coordinator, and that's just through standard Postgres protocol. So any of your libpq, your JDBC drivers, or pSQL, any of that is all just works out of the box. The coordinator transforms the query into a distributed query, executes it in parallel against all the workers. When the data comes back, the coordinator merges that information or does any aggregations that is left needed to do, and then returns it to the user. The coordinator really doesn't own any of the data. There are cases where, depending on your setup, maybe you want some very small tables that aren't distributed, and they can live on the coordinator because it is just a Postgres server. But really, all of the distributed data is going to be on all of these worker nodes. And the worker nodes contain many different shards. And so maybe you have, let's say, 8 worker nodes here, and each one of them might have themselves 8 or 16 shards, depending on it. And to give a more concrete view, if you were to connect to the coordinator and say \d, which lists the tables that are in the Postgres machine, on the coordinator, you see just normal tables. But if you connect to one of the worker nodes and do the same \d, you see all of the individual shards as they're numbered. And the way that the sharding works is using the built-in Postgres hash function on the data, on the shard key. We split up negative int max to positive int max, and wherever the shard ends up having to be, according to this metadata table, knows what shard the data is going to go to. So for the rest of the talk, there's many, so that diagram, it seems simple. We just split the data up and you get it back. But as it turns out, once you actually dive in, there's a lot of complications the more you look at the problem. And scaling SQL is a challenging task. And we're going to look at 3 different aspects of that in the rest of this talk. One is high availability. The other one is, okay, now you're actually going to build a distributed database. How do you go about doing it? What parts of Postgres do you need to modify? What do you have to think about? And then the last one is distributed transactions. A lot of the NoSQL databases, in order to get massive scale, just say you can't have transactions at all. But if you want to have a nice SQL database, like giving up transactions is sort of a non-starter. And the last part of the talk will look into how transactions work. So one of the most common questions I get when talking with people about Postgres is, what is your high availability setup? How do you do it? And so on. And especially if you're going to be running databases on cloud infrastructure, which is somewhat less reliable than on premises, you want to really have a good handle on high availability and disaster recovery. So most of Postgres high availability uses the built-in streaming replication, where there's one primary and one or more read replicas that are copying off of that primary. But in Postgres, this brings a couple of challenges. One, all of the entire state has to be, the first one, most Postgres clients only know how to talk to a single endpoint. And so when it fails over, you need to reconfigure that one to talk to the new server, or you need to do something else, which we'll talk to on the next slide. And the second one is that Postgres does replicate the entire state, and that makes bringing up new replicas potentially very expensive. And so Postgres has a large ecosystem of clients. There's many different clients that can connect to it, and they all have to be sort of on equal footing. We want to be able to swap out replicas during failover very easily. And some of the clients these days can actually have a list of IPs to connect to. JDBC has had it for a while. Postgres 10, the libpq in that, you can also give it multiple connection strings, and once the first one dies, it'll go to the second. But that requires that as you started your application, you know where all of your read replicas are going to be. So if your application is running and you make a new replica, it won't be available in that list of connection strings when you booted the application for the first time. And so in order to solve this in a generic way, you need to fall back down to networking primitives. This example here shows how an elastic IP failover would work in Amazon. Or you can use DNS or some load balancer or perhaps PG bouncer to manage doing the failover to another thing. In this case, with the elastic IP failover, what we do is when we want to destroy the old primary and switch over to a secondary, we rip the EIP off of that machine and put it onto the new one. And that way, that combined with shutting off the old machine and some other techniques to make sure that all the traffic is being going to the new computer. But there's three methods for sort of dealing with HA and backup in Postgres. The first is just use right out of the box a streaming replication. The second is to do a volume-based replication where you're actually using the underlying disks and ignoring that Postgres exists at all. And then the third is to take the write-ahead logs and treat that as a first-class citizen. And so this first approach is the most common. The primary node has all of the tables data and the write-ahead logs. The write-ahead logs is a system in Postgres that's a couple of releases old now, maybe close to 8 years, where as the data comes in, it gets written to the write-ahead log first, and that's like a log of the physical changes that need to happen to the database files, and then it writes it to the actual database heap. And then, so you have a secondary up, and you can stream those WAL files to the secondary and apply them. The problem, though, here is when you have to bring up a new one from scratch, you need to copy over the entire base backup of the machine over the protocol into the new machine, and that can cause some extreme load on the primary. And so that makes you sort of hesitant to be spinning up replicas all of the time. The second one is the disk-based approach, which is what both RDS and the Azure Postgres preview use. What's nice about how the way it works is they synchronously replicate the file system over to another set of disks. What's nice about this is it's sort of database agnostic, so they can use the same system for Oracle, for Postgres, for MySQL, for SQL Server, and so on. But this does require that you both replicate the WAL and the data directory together because both are needed for Postgres operation. And then also the other downside for this is that all the operations have to be sent synchronously over the network because having anything out of order would cause corruption. And then finally, the third way turns the replication and disaster recovery process into the same thing by taking the write-ahead log files and making that a first-class citizen. So with this, it's similar to the first one that we're using the streaming replication system, but we're taking the WAL files as they are created and putting them off to S3 or whatever like object store that your provider has. And once it's there, on top of that, once a day or so, you take a base backup and upload that. Now this you can do in a way that doesn't impact the primary as much by uploading it at a very rate limited way. And so you can have the cost of that be fairly low. And now, once you have the base backup and the WAL file over on the side in some other store, you can spin up read replicas without impacting the primary at all. And this enables a couple other interesting things. You can create a fork of your database. Let's say you want to experiment with some data migration. You can create a copy and experiment on that and then throw it away. Or because you're replaying, you have the history, all of it on S3, you can stop replaying partway through and sort of go back in time and have a point-in-time recovery. And so this table just kind of summarizes those differences and just as a summary for later. And if you want to do any of the last things the last way with putting the files up to S3, these are two projects that we've been involved with, WAL-E and then its sort of newer successor WAL-G. What they do is they handle that sending the files to S3, reading them back down, and so on. WAL-E's been around for 7 years we built it at Heroku Postgres, and then WAL-G is sort of a newer version written in Go that is a little bit, or it's significantly faster, but it's less battle tested, so it's not really ready for production quite yet. And so all three of these replication methods replicate a database state in full, which is good. But once your data starts getting bigger and bigger and bigger, the time it takes to do that starts taking longer and longer. Like there's really no way around that. And so what's nice is if you have this as your backing, as your base, and then move into a sharded world, because then you can use this on each one of your shards and have quick recoveries, quick failovers, but then also grow out to bigger and bigger sizes. And so now you're looking at finally distributing Postgres into turning it into a distributed database. But one of the problems is that the tooling around Postgres, both externally with all the different tools and third-party things, but also internally inside Postgres, all the different types of queries you can do, transactions, and so on. It makes distributing Postgres very difficult. But there's three ways if you're going to make a distributed database. You can either perhaps make it from scratch. That has some complications. You have to build your entire storage engine. You have to build your entire query engine, and so on. You can do some sort of middleware sharding either as a separate component, or most commonly I see people do it inside their app of saying, okay, client 1, all their data is on machine 1, client 2 is on machine 2, and so on, modulo the number of machines. And then the third one is to fork your favorite database. Postgres is often a very common target for that because it is sort of a very modular system. The problem with that is over time the features diverge and you end up being your own database because it just gets harder and harder to keep your changes applied to the fork of Postgres, as Postgres has a release every year. This is one of the queries that early on some of the founders got not exactly the same query, but something like that. And they're like, the client wanted, like, hey, can you make this work in Citus? And at that time, save points weren't available. And so the team looked at that and they're like, who's doing all this work with save points and rolling back sort of nested transactions? Like, who would write a query like that? It turns out that it wasn't actually a person. It was just the Ruby on Rails testing framework, adding in all that. And they realized because of this, you can't really go halfway if you're going to build on Postgres and turn it into a distributed database. You need to support all of the features, both the current features, new features as they're coming out, clients, ORMs, and so forth. But at first, it was a fork of Postgres. It's an extension now, but it was a fork. And this is a sort of a diagram of the internals of Postgres. And because it is a very modular system, it made it easy to start that way. For example, if you're going to distribute the create index command, where you would hook in is the DDL and utility processing in the middle. And you can just hook into that one part and then do your distributed work there. The planner and executor are more complicated, and they were very coupled to each other. And also at the time, they made a lot of assumptions to the storage layer itself. And so they started working on a two-stage query planner and executor. So when you send a query to Citus, what it first does is parse and then semantically verify that it's an OK query. And Postgres does that work. And then Citus comes in, hooks in there, and sees, does this query touch any of the distributed tables? And if so, then it starts doing its work. It uses the metadata table to plan the query to see, let's say it needs to touch 3 shards and 2 of them happen to be on one node and the other one needs to be on the second node. It can recognize that to minimize the total number of, the total amount of network I/O. Because there may be 3 or 4 ways to actually execute a query. In a distributed environment, network I/O is almost always the slowest part, and so you want to minimize that as much as possible. And then what happens is Citus then actually, after it breaks the query up into what it's going to send to each of the nodes, it'll deparse that back into just a regular SQL string to send to the Postgres nodes. And this has a number of advantages. One, it separates those two parts, the planner and then actually executing it. And that allows you to test both of them in isolation and also introduce logging to see what's actually being sent. And second, the Postgres at the receiving node can do its own optimizations. And because all it is just seeing just as a regular Postgres query, so it can do its own optimizations of what indexes to use. It can make its own decisions there. So going back to the diagram, let's look at an example query. So this is doing a select average on revenue. And there's a lot of aggregate functions that don't distribute nicely. However, average is one that is distributable. And so what happens here is it'll receive the query, deparse it into what needs to happen, and then on each one of the nodes it'll do a count and a sum, and then they'll all do their work in parallel and send the count and sum back to the coordinator. The coordinator, once it gets it, will combine that back up into an average, and then as a final computation, and then send the results back to the client. One of the other things that, now that you understand sort of that architecture that you can do, is the only thing special about the coordinator there was that it had the metadata table to know where the data lived. If you replicate that metadata to each one of the worker nodes, any one of those worker nodes can now be sort of a coordinator for running a query. And if then you connect to one of those randomly, or you set up like a round-robin DNS, now you're in sort of like a masterless environment without that much more work than having a single coordinator. And that's by having the design of the coordinator not really owning any of the data, just being responsible for aggregating the results from all of the different workers. And then so over time, we worked with the Postgres core team to add in enough extension hooks so that instead of being a fork, we could be an extension. And so this is nice. Now Postgres, now Citus is just a shared library that's loaded inside Postgres. And all you have to do is say create extension Citus, and it loads all of these different hooks in to turn it into a distributed database. So the last part is one of the more interesting parts of the talk, in my opinion. So handling distributed transactions in a relational database has many more complications than just doing it in a single node. So distributed transactions are a heavily researched area. You want, depending on the isolation level, you want to be able to start a transaction, do some work, and not have it yet be visible to other actors until you either commit or roll back. And there's two challenges here. One is consistency, which is one that everyone knows about, is very heavily talked about in this sort of area of research. And the other one is locks, which doesn't really get the same sort of attention, but is just as important. So what happens when one or more machines that are participating in a transaction fail? You need to have a good consistency story. There's several popular algorithms. These are just three. The first one, 2PC or two-phase commit, where you go in and check in again afterwards before you know that you're actually going to commit. This one has a downside that it requires that all participating nodes have to be online for any progress to be made. The other two, Paxos and Wrapped, have more of a consensus where only some majority subset have to agree that this was committed for it to go. So we looked at both of the 2PC and also Paxos, and we actually released a Postgres extension called PG Paxos, which implements Paxos in Postgres. But we ended up going with 2PC because it's already in Postgres, and the downside of the nodes having to all be online is less of an issue for us because of the high availability story in part one. the nodes, when they're down, are typically down for such a short amount of time that the downside of them requiring everything to be up is less of a concern. So the concurrency, concurrent transactions want to modify the same data. You need to fall down to locks. And at the core, locks are very simple. You just say, I'm accessing this data, no one else can touch it. Prevents two transactions from modifying the same data concurrently. But the problem you run into very quickly is when two transactions try and grab the same lock. And you can run into the problem of deadlocks. You need some way to deal with this. Postgres has built into it a deadlock detector, and we're going to see how that works. It looks like that did not go. Imagine very good SQL lines. That's very good code. Yeah, I don't know what those lines are on top. So anyway, there's this other one down here. Once the first one is modifying where x equals 1, it grabs a lock on that row. And when the second transaction tries to modify it, it's going to be stuck waiting for the first transaction to finish, and then it can proceed because the locks are released at the end of the transaction. Now, if two transactions have different filters, they can run concurrently. So the first line here, the left one is accessing where x equals 1, and the second one is where x equals 2. That can happen at the same time. But once the second transaction tries to touch where x equals 1, it's going to start having to be put on hold until the first one finishes. This is all fairly straightforward. The problem, though, occurs when they're in different orders. And so here, the left one can take the lock on where x equals 1. The right one can take the lock where x equals 2. But then their next thing that they're going to do is try and access each other's locks. And now we're in a deadlock situation. Neither of these transactions can proceed. Neither one of them is going to suddenly gain control and take over. And so you need a way to get out of the situation, because other queries might be coming in and taking locks on where x equals 1 or where x equals 2, and just compounding to the problem where everything starts escalating to a full system outage. And so Postgres, I forget when they added it, but Postgres has a deadlock detector. And the way that it works is anytime that a transaction has been waiting for more than 1 second, it'll run the deadlock detection. What it does is it generates a graph of all the locks and then turns it into a graph of transactions where each transaction is a node, and then the edge is if it's depending on this other transaction to finish. And with that, if there's a cycle in that graph where one is waiting for the other to finish and that one also is waiting for it, then we know that there is a deadlock, and Postgres will cancel one of those transactions, freeing up the locks and allowing the system to continue. And so then one of the transaction has to die, and then the other one lives. So we need to do the same thing in Citus, but it's more complicated because of the many more machines that can possibly happen. So in the simple case, if distributed transaction 1 and distributed transaction 2, D1 and D2 there, both happen to have all their data happening on node 1 and nothing on node 2 or node 3. For example, one of these multi-tenant applications where you shard based on the tenant or the customer. If it's the same customer and all the data happens to be on the same server, Postgres deadlock detection works just normally. The Postgres down in the worker node will detect the deadlock in the same manner as single node Postgres, cancel one of the transactions, and that will cancel it back on the coordinator. That connection will receive an error, and the other one will continue. The more complicated situation is this case, where distributed transaction 1 is executing fine on node 1. It acquired the lock first on node 1, but it's also running some work on node 3, but it didn't grab the lock first there. Distributed transaction 2 is sort of the reverse situation, where it managed to grab the lock first on node 3, but not on node 1. And so there is a deadlock here, but in any one of the spots, the Postgres in node 1, it doesn't see a deadlock. The Postgres in node 3 also does not see, it's impossible for it to notice that there's a deadlock. And so you need to have something sort of outside the system to look at everything and notice that something is wrong. And so Citus 7 added a background worker that if a transaction's stuck, it'll dial into all of the machines in the cluster, build up a lock graph of everything, and then start looking for cycles. If once it notices what's waiting on what other transaction, it can have a picture of the overall system, look for cycles, notice a deadlock, and then go in and cancel one of the transactions, which then propagates back up to the coordinator, kills the query, and so on. And this is a necessary part of having distributed transactions. So most of the things you see in this sort of world of distributed transaction is always focused on consistency, which is an interesting and difficult problem. But the sort of distributed, if you're going to have transactions, you're going to also have deadlocks, and this sort of deadlock detection is also an important thing to worry about and think about, but it seems to not get as much attention as some of these other areas. So we talked about 3 different technical parts of scaling SQL: the replication and high availability, the extension APIs, where to hook in, what to think about when distributing SQL, and lastly, this distributed deadlock detection. And back when we started making Citus, sort of the common catchphrase was, "Oh, SQL doesn't scale," and it seems like whenever there's a really hard problem, it's easy to just trivialize and say, like, "Oh, that's impossible." But really, this is, in computers, things can be very tough, and you can break it down into small problems. We just looked at 3 of them today. There's, many more problems. And so really, scaling SQL is not impossible. It's just hard. But hopefully this gave some insight into how to do it. Thank you very much. This is some contact information, and I appreciate your time. Thanks.
Ask some questions.
Hi, Will. Thank you for your pretty interesting talk. But I have a few questions
Sure.
regarding this product, I believe. The first one is related to coordinator node. As I understand here, it's like entry point for all requests you will make against your cluster.
Yeah.
So the capacity of the whole cluster is limited by this coordinator node.
Yes.
Right?
Yes. However, one of the, I don't know if I can quickly go back. One of the ways which you can do is there's this thing called Citus MX, which allows you to connect to any of the worker nodes and have them act as a coordinator. And so in default, yes, you just connect to the coordinator because that's usually enough. But we've seen if you need to scale out your writes a lot, then you might want to use the Citus MX to connect to any of the individual worker
So
nodes.
like every node could be a coordinator
Yes.
in this case.
Yeah, the only thing that is extra special about the coordinator is if you want to create a table or modify a table, those operations need to be done in a centralized place. But for normal DML, you can do that anywhere across the cluster.
Okay, cool. And another one question is regarding when I do select for some partition, and by some reason this partition node is down, how fast it will be recovered and I get my data for request?
Right. So if one of them's down, that any queries that touch that will block in the coordinator for the underlying server to be replaced, and that depends on what method you're using for high availability. In Citus Cloud, the one I work on, we notice within 30 seconds to a minute, we want to make sure that it's not just a network blip, so we check a couple times and then we swap
like
the EIP.
30 seconds, it's already like lost a request.
Yeah, probably.
So
So you probably you can dial that and be more hair trigger on your what you want.
Yeah, I mean, like this availability in this case is a little bit less because you have a point, you have get a chance when you will not reach your data until the node will recover it.
Right. Yeah. Like if you're running this on your own hardware and you can be sure more often, like the first time that you notice that the database is down and you can be absolutely certain that it is down, then you can trigger failover faster. It's just on Amazon we've seen more transient problems and we don't want to go through an entire replace unnecessarily.
Cool.
Hello, I am Artem. First of all, thank you for the talk. My question is, can it scale elastically? So say I have lots of data, lots of incoming transaction, and then here is Black Friday next week. So can I increase the number of shards and nodes, rebalance the data temporarily, or not temporarily, online without downtime?
Yeah,
Thank
there,
you.
there is a rebalancer product that will move shards over one at a time. Reshard, like adding more shards, is difficult because then you need to, move part. You have to rip it apart and move parts of the data. Technically, it should be okay to if you wanted to double the shards. We don't have the tooling for that quite yet, but moving already existing shards onto new servers is a thing you can do.
But I can say pre-create, say not 10 shards at
Right.
10 hosts, but say 30 shards at 10 hosts, and then just rebalance them across more nodes if necessary.
Exactly. Most of the time, we see people create. Maybe they have 8 servers or 10 servers, but they create 64 or 128 shards, and so one server might have, 10, 20 shards, and that's okay.
Okay,
Yeah.
thank you.
How does deadlock detection work in Citus MX?
It's the same. The only difference is it's when that coordinator notices that one of its transactions is blocked, it does the deadlock detection. So each one of them that has it. Yeah.
And I have a small question. And do you support distributed joins?
Yes. And so if there's sort of two concepts here. One is if the two tables happen to be sharded on the same key.
Yeah.
If it's local, the join can be done locally. If it's not, it can be repartitioned for that join. That is an expensive operation. So you don't, like if that's a common path, you might want to model your data in a different way so that you can get the joins to be co-located. The second thing is if the other table is a small table that changes relatively less, that one can be copied onto all of the machines, and then it makes it a local one.
Hello, I'm here. Thanks for presentation. I have a question. When I use the client like JetBrains, DataGrip, or something like that, is there the prepare statements problem like with the PG bouncer by the using JDBC or something like that? Maybe Citus have his own driver.
Yeah, so we would, right now, since we don't have our own driver, any problems like that would probably be similar. I'm not, unfortunately, I'm not too experienced
So we should
in.
go to master or something like that?
Yeah, so like, yeah, if the prepared statement is on the, if you create it, well, so prepared statements are what? They're per session. And so if you're if you're using a bouncer, you're going to run into that same problem no matter what with us.
Okay.
Yeah, sorry.
Thanks.
Hi, I want to ask that right now we have a problem of high availability and distribution of Postgres, and like some people are trying to solve it by container orchestration, so trying to put the Postgres in a container and manage them in Kubernetes, like in stateful sets, to check some state and balance between the nodes, making the same storage. And I just want to know your opinion. What do you think? Is it like, how is it possible, for example, is it possible actually to integrate the Citus into this environment, and is it actually reasonable to use some sort of schedulers to distribute the queries and load and SQL databases?
Yeah, that's interesting. We've looked into it a little bit, but not enough to know definitely how much it helps. Yeah, one of the things is like containers are good for applications, but for databases, I'm not myself so much sold on it, because you have to also have all the state somewhere, and being able to move that around, because it's just so heavy, makes it a little bit less flexible than like an application, you know, that's stateless, moving that around. That said, if you do have external network attached storage, that makes it easier. Yeah, basically, I'm not. It's maybe a good idea. It's maybe not. Like, I'm not sure. Sorry for not a better answer.
Okay, thanks.
Hi. During your talk, you compare two-phase commit, boxes, and draft.
Yeah.
And you said that you pick two-phase commit, right? So I wonder which design decision was there, because two-phase commit is a blocking protocol comparatively to other two, and not so popular now. Just curious why.
Yeah. So the two reasons that we went with that is, one, it already is established inside Postgres, and it was easier, you know, less maintenance work. The second is, even though it is blocking, we sort of assume that everything is going to be up, so that downside isn't as painful as it is in other systems.
Do you have plans to move from two-phase commit to something else?
No hard plans, but we are definitely you know, open to exploring things as they come up.
Okay, thank you.
Yeah.
Есть еще вопросы?
So I was wondering that you providing your solution on Amazon, and they have some kind of RDS Aurora around Postgres. Can you tell some main difference between both solutions?
Yeah, for sure. So Aurora, if you just need to scale out how much data you have, it's good. The problem though with Aurora is there's still only one machine that's doing the reads, and so you can't keep as much data cached in memory. Whereas with Citus, because each machine owns its own subset of the data, all of that can be cached, and you can use all of the memory and all the CPU in your cluster. So you can scale out not just disk, but also memory and CPU. Yeah. All right. Thank you, everyone.